Homework then. You didn't have it out, so I skipped over it. So I can give you a 0 again. Alright, so when you are making an equation for sine or cosine, you can always pull out the b value and use the phase shift in the equation. When you write an equation for sine or cosine, you can look at either a sine graph or a cosine graph and get the same information for A, B, and D. If A, B, and D are going to be the same when you write sine or cosine. The only thing that changes is the phase shift. So if you're looking to write a sine equation, where does the sine start? In the middle. It starts on the sinusoidal axis. So you need to pick a starting point, and then you need to make sure that you follow it till the end of what sine should look like. And a sine graph has a max and a min. That's what a sine graph looks like. It has a hill and then a valley. So if I'm looking at sine and I'm picking a place where it's in the middle, and then it has a hill and a valley. Because in order to get the period, you need to make sure you're grabbing like the whole entire portion of the graph that correlates with sine or cosine. So cosine goes from peak to peak. The sine has to have a hill and a valley. So I have that kind of highlighted up here in blue. The second thing we need to figure out is, again, we said the points were small. Jacob said we're counting by pi over 4. This back here is pi. This here is pi over 4. But I need to know what that point is. Jacob, how do you figure out that point?
So I just knew that it was pi over 8, but how you would find it is you would see that it's in the middle, and you would divide times pi over 4 by 2.
Yeah, so everything is like halved in the middle. The circle has 2 halves. Each one of these, it's not like one point is closer than the other point. They're all equally spaced. So if you have a point at 0, and I have a point at pi over 4, the value in the middle is truly going to be in the middle. It's going to be half of it. So that first point for sine, bless you, is pi over 8. So if it starts at pi over 8, that's where my sine graph starts, on the middle, in the sinusoidal axis, that is also the phase shift. So wherever you pick your graph to start corresponds directly with the phase shift. If it was cosine, it would start at the high point. Now it's starting in the middle. So my phase shift is the first point that I'm choosing there, pi over 8. The amplitude, that's the stretch. So from the middle to the peak, Maggie, how high is it stretching? 2. So the amplitude is 2. This didn't ask for the sinusoidal axis or the d value because it's just 0. So that's why it didn't ask for it. So the other thing we have to calculate then is the period, which means from here at pi over 8 to this point, what is that distance? Does anybody know what that other point is, where it ends? So it starts at pi over 8. Jacob is going to?
It's going to end at, it's going to have 3 pi over 8. 5 pi over 8.
5 pi over 8.
That's what I meant.
Okay. And the reason that happens is because each one of these is really pi over 8. Like if I was graphing it, I'd count by pi over 8. So pi over 8, 2 pi over 8, really pi over 4, 3 pi over 8, 4 pi over 8, 5 pi over 8. Kevin?
If it's easier, can you find the period for the cosine graph?
Yes.
That's what I did.
If it's easier to look at, you can find the period for cosine. So if you say, hey, it's really easier to find the period of cosine because we have a pi over 4 and a 3 pi over 4, again, the periods are the same because both of them spin around the circle once, which is initially 2 pi. So you can look at either one. And how much easier for you to kind of view. Yeah, sure. So if our period is from pi over 8 to 5 pi over 8, or pi over 4 to 3 pi over 4, the entire distance should be pi over 2. That's the stretch from one to the next, so the full cycle of the graph. And then we use that to find b. So pi over 2 is the period. It's equal to 2 pi over b. So Kevin, the b value is 4. Remember, you need to find b. You can't plug the period into the equation. You need the b to plug it into the equation. Questions? So So we have everything we need. We don't have a d value. We can write our equation. Amplitude, we have a sine graph. Period is 4. And then in the parentheses, the phase shift is pi over 8. Shifting right from 0 to pi over 8. Questions? If I wanted to write a cosine graph, I'd still have a 2. We'd still have cosine here, not sine, changing it. We still have a 4. Where would the starting point of cosine be? Or,
So it would start at pi over 4. But I have a question.
Sure.
Couldn't you just do y equals negative 2 cosine 4 and then just x?
So another graph or equation could be negative 2 cosine 4 and then just x. Because he's saying let's not have a phase shift and start it at the low point. So if cosine starts low and ends low, it's a negative cosine graph. If it starts high and ends high, it's a positive cosine graph. Very similar to quadratic functions. If I have a positive x squared, it's up. If I have a negative x squared, it opens down. So positive cosine graph, positive number in front. A negative cosine graph starts low and goes high. Positive cosine graph starts high and then it moves low. Questions? There are so many equations you can write for one graph, whether you're looking at sine or cosine. The more periods that are given, the more equations that you can create. Questions?
Do secant and cosecant have graphs?
Yes, that's what we're going to graph next week.
Are they like side?
No, but they're kind of like inverses of what we have, reciprocals of what we have. So one picture you can write sine or cosine for. Next week we're going to actually graph tangent and cotangent. One tangent or cotangent graph, like one picture could represent tangent or cotangent, like one picture represents sine or cosine. So trig functions are a little different because they do have relationship, like the co-functions, the relationship functions that are together. Whereas an x squared function is only a parabola. And a parabola is only an x squared function. There's not another function that's corresponding with that when you look at the graph. So I'm going to talk a little bit about the two homework problems they were asked to complete.
I have to have one more question.
Yep.
So will there ever be a graph, like, or is there a graph where the amplitude starts out smaller and gets bigger?
No. No, because then like your equation is like changing. You have then a second equation. So you'd have a totally different equation for that next section of the graph. So sine graph and cosine graph only has the same amplitude for the whole line. All right, so looking at the Ferris wheel, it seemed like throughout the day, a lot of people were trying to use the picture to create an equation, the picture of the circle, instead of trying to make a picture on your own, a graph on your own, and trying to use the graph to create the equation. And it looks like the period is definitely something that I saw was different in a lot of people. A lot of people have different values for the period. So we're on a Ferris wheel. The little point here represents the cart, where you're like getting onto the Ferris wheel. And that's where you're sitting down. And it says here, t is the number of seconds that has passed as the Ferris wheel has started. And again, we're always trying to measure distance. How far is something off the ground? So you have your phone, you decide to get in that, decide how much time it is. You want to know, you're sitting on the Ferris wheel. How long does it take to spin the whole way around? So you start it, you get on, and you notice that it takes 3 seconds to get to the top, which is pretty fast. And once you're at the top, you're at 43 feet above the ground, which actually isn't very tall for a Ferris wheel. So 43 feet, probably a little taller than our building. Not that tall. But I know then, if it's 3 seconds at the top, that makes a point on my graph. So at 3 seconds, I have the point, the max, up at 43. So that's like the first thing I can graph. 3 seconds, I have a maximum value. If you continue to read on, it says the wheel makes a revolution once every 8 seconds. What does that mean? If something makes a revolution once every 8 seconds. Maya, what's it mean?
To get back to where it started.
Yeah, so if I'm at the top, to get back to where it starts, I have to go 8 seconds to get back to the top. So if I knew at the top it took 3 seconds, and I want to get back to the top, I would then be at 11 seconds. So in 11 seconds, we're back at the top because it took me 8 seconds to get there. So I noticed at 3 seconds I was at the top, spun around, and now I'm back at the top 8 seconds later, but now it says 11. So now I have a distance from one max to the next max. That's going to be our period. So the distance from peak to peak. So continuing to read the last sentence, the diameter of the wheel is 40 feet. So that means that at the top here, we said that was 43. If the whole diameter is 40, where are you then at the bottom of the circle? Odette? 3. Because 43 foot, Ferris wheel diameter is 40 feet, so at the bottom, I must then be still 3 feet above the ground. So I know that I have to have a point at 3 feet, and that's going to be in the middle. Because if it takes 8 seconds to go all the way around, half of that I should be at the other half of the circle. So what would the number be? How many seconds would it be if I'm at the bottom of the circle, Jacob? 7. Because if the entire distance or time that it takes to go around is 8 seconds, at the top, I go 4 more seconds, I'm at the bottom. 4 more seconds, I'm back at the top. So I can connect these 3 points. Cosine should look kind of like a U. Maybe. Oop, there it goes. So now I have a cosine graph. I really didn't rely that much on that diagram besides kind of thinking about that stretch between my max and the min. And that was really just using the diameter. So now that I have a picture drawn, from this picture, whenever we have a graph, the first 2 things we try and look at are D and A, because those are really the easiest things to visually see. If you have D, or if I'm trying to find D, and I know the max and the min, what does D represent? The sinusoidal axis, which is the middle of the graph. It's the center. It's the midpoint. So if you know the max and the min, and you add them together and divide them by 2, you get the center of the graph, which is 23. So at 23, we have a sinusoidal axis. That's where the graph would cross through the middle. That's how we would find that in any of the other graphs that we've done. So you don't need to use the diameter. You don't need to use the radius. I've used nothing with that diagram to figure that out because I have my max and my min drawn. The sinusoidal axis is in the middle of them. Once you have the sinusoidal axis, you can visually find A. How is A related to my graph? Where would the A value be? Kevin?
43 to 23.
Yeah, 23 to 43. So this distance here is A. The stretch vertically from the center to the top. Well, that stretch is 20. It's also the radius of the circle. So the radius and the amplitude are the same, but the stretch from the center to the top is A. And then the last thing that we need is our period, and how long does it take to go around the whole circle? From your starting point to then back to that starting point. How long did it say it took? 8 seconds. So if we know that our period is equal to 2 pi over b, b should be pi over 4. So people have different numbers there. So if you're using an 8, you don't have to do anything fancy with the 8. That is your period, the time it takes to spin around once. Yesterday's problem, we had to convert it a little bit because it spun around the circle 6 times, I think, in a minute. And we needed to figure out how much time that was in seconds. This is already in seconds for us. Questions? So to write an equation, it looks exactly like cosine. So we have our amplitude. Looks identical to a cosine graph because it starts at the max and ends at the max. The B value is pi over 4. D is 23. And wherever you have your graph starting, that's the phase shift. So the graph starts at 3. That's my first point. So 3 is our phase shift. Questions? So the following questions underneath, it does say to predict. And yes, you do want to use your graph to help you, but you also are going to plug it into your calculator. And this is where I saw everybody have totally different answers. So if you can take out your calculator, please. The first thing you have to make sure your calculator is in radians. So it has to be in radians because the angle here is radians. We use 2 pi, so the calculator has to be in radians. The first one wants us to figure out when time is 6 seconds. So just like a visual. Here's 7 seconds. So we want to figure out when time is 6 seconds. So I don't know, probably somewhere like in that ballpark, maybe a little left, a little right. But it's going to be under 23, above 3. So if you look at your answer, it should be less than 23, but a little more than 3. Because 7 seconds is at 3. So it's going to be a little more than that for 6. In our calculator, we have 20 times the cosine, pi over 4. 6 minus 3 is 3. You need to make sure that you have a group of parentheses around both of these numbers. So my suggestion would be to calculate this first in your calculator separately. So right now, type pi over 4 times 3. And then, now that you have that number, you're taking the cosine of the number that you got here. Whatever that number happens to be. But use that second answer function. Does everybody know where the second answer button is? So 20 cosine second answer plus 23. We should get 8.86. How did we do with that? Does that make it a little better? So like when you look at your graph then, so my line was a little off. It makes sense that at 6 seconds, it's going to be, it should be a little above 7. So the next one then said, what, 4 1/3? So at 4 1/3 seconds, that's going to be closer to 3. It should be at 33 feet. So now I'm closer to 3 than I was to 7. So yeah, that could be at 33 feet. But using the graph in your answer, make sure it makes sense. So I would separately do pi over 4 times 1 1/3. Like do that number first, and then use your second answer function. Way easier to do it that way than to like plug in 15 parentheses and making sure you have everything right. For 9 seconds, it should be at 23 feet, and then 0 seconds is 8.86 feet. So 6 seconds and 0 seconds actually was at the same point on the Ferris wheel. They ended up being at the same place, just across from each other. Questions? Why is the Ferris wheel above 0? Odette? Yeah. So it can spin around instead of hitting the ground and crashing while you're on it. So if you had it at a negative number, then it's like going into the ground and digging up dirt. Then it's really fast. Questions? Yeah. And maybe if you had like the ground dug out. Yeah. All right. I want to quickly go through the next one. Again, I saw a couple of different answers, so I want to make sure everybody kind of understands how. Like try and use a graph after you have the graph to create the equation instead of trying to create the equation and then like making a graph. So this problem here, again, always measuring distance, whether it's distance to the ground or in this case it's distance to the top of the ceiling, but we're still measuring distance of the hour hand. Which one's the hour hand? The small one. The only one. Well, there's a seconds hand and there's a minutes hand. Not here, though. Yes, this is true. Not here. So it says 12 o'clock, which is the tip of the hour hand, we're at 23 centimeters from the wall, which mine is more. Mine's probably like 2.5 feet, but 23 centimeters. Make a scatter plot, which is just a bunch of points, to show the relationship between elapsed time and the distance between the ceiling and the tip of the hour hand. So if you look at the first diagram, elapsed time means as time passes. This is my starting angle. Our starting angle is 0. Time is 0. Time has not passed. So that, even though, yes, you're saying, yeah, but that's 12 o'clock. Yeah, but we're talking about time passing. So I'm starting at an initial value of 0. At the initial value of 0, what is the distance from the tip of the hour hand to the ceiling? Well, 23 centimeters. So I'm going to put a point that corresponds with 0 and 23 centimeters. How much time has passed at my next diagram? Aggie? 3 hours. Remember, this represents time passing. So it's hours. So this is 0 hours, no time has passed. Now, if my little hand, my hour hand, is pointing to the 3, that's 3 hours later. So at 3 hours, now it's right here, we're figuring out this entire distance. What would that distance be? So 15 and 23 is 38. So now I have a point at 38. Okay, my next one, how many hours have passed? 6. And if I'm at 6 hours, I'm at the bottom of the circle, which means I have the whole entire clock and the extra 23 centimeters, and that's 53. So if I continue spinning around, now I'm at 9 hours later, we come back down. 12 hours later, back to where we started. 15 hours later, goes back up. So here's the graph. You would connect it with a curve because we're trying to make a sinusoid. I wouldn't connect each one with its own separate line. It's a curve, it's smooth, it's continuous, it's still circular, we're just spreading out in a horizontal format. Questions? So this y-axis is really starting with 0. It's just my diagram here didn't connect to the y-axis to make the circle separate. So when you go to make your graph, or when you go to make your equation, now you have a picture. You can visually see the middle of the graph because the center of the graph is 38. So now I have my sinusoidal axis. I know A is 15 because that's the middle to the top. And I know the period is the time it takes to spin around the clock. How many hours would it take to go the whole way around the clock? 12. Remember, it's time in hours. So that means 12 is equal to 2 pi over b, or pi over 6. Questions? I think a lot of you are trying to make it into decimals, trying to think that maybe it was minutes, forcing it to be some type of angle on the unit circle, when we're talking about time, like actual time. So to create the equation, we have 15. We're asked to write sine and cosine. And what is it, 38? And then I have 15 cosine pi over 6. You need to pick a point for the sine to start, pick a point for the cosine to start. So the sine starts on the sinusoidal axis. So right here, phase shift for sine is where it's crossing the sinusoidal axis. That's 3 hours after the initial starting point, 3 hours later. What could you use for cosine? Looking at your graph.
0.
You could use 0 and make it a negative 15. So if you started at 0, you would make it negative 15. Because it's starting down. So remember, a normal cosine graph starts up high. But if it starts at the lowest point, then you would make it a negative 15. What could you use for a phase shift for cosine if you wanted to start up high, Odette? You could use a 6. Questions? So I could start cosine up here at the top, and then it would have a phase shift of 6. It would be a negative cosine if you're starting it at the bottom. Questions? So if you flip in your packet, just flip the page over and look at the back. I have sketched the function first here to force you to graph it first and then try and use the graph to create the equation. So this is talking about a tsunami or tidal wave, which we've had multiple tsunamis occur within the last handful of years. So tsunami, earthquake in the ocean, it causes a pretty much ripple effect, pulls the water away from the shoreline, and then it uses all that momentum and comes crashing down. And it has destroyed islands before. So it could be catastrophic, or if it was just a little thing, it doesn't have to be so bad. But just think like if you're on the beach, you're really having like waves come and crash. They pull away from the beach and then they come crashing in. So we're talking about here the water going down first from the normal level, rising back to normal, and then going above that amount. And it says the period is 15 minutes. So the amount of time that it takes for it to have a full cycle of pulling away and coming and crashing on the beach again is 15 minutes. That's a pretty long period of time. So this is like a pretty big tsunami happening here. It says our tsunami has an amplitude of 10 meters. That means it's going 10 meters above normal. So think if there's a wave that's 10 meters high, that's pretty tall. So not your typical wave that you would see at the beach. We're at a pier at Honolulu, and the normal depth of water is 9 meters. So that's where the water is normally resting. That's your middle. So 9 meters is the middle of the graph. That's where it's normally resting. It's not resting at 0. It's actually above what we would say sea level. So 9 meters is like the middle where the water is just resting right now. So you're going to try and complete that, Jacob. The next page on page 23 is a Tarzan problem. That's not due till Tuesday, and I'm going to collect that from you. And it is like if you're on a swing, it's a swinging motion. So think like every time you hit the max, you go down, you hit the next max. So like as a swinging motion, you're just continuing that swinging motion horizontally to create a graph for a curve. And then if you flip all the way to page 33, page 33 is more just to kind of get us started. It's just using your calculator and filling out that chart, which we did for sine and cosine. That shouldn't take you very long. It's just plugging those angles into the calculator. Make sure your calculator is in for you. We're going to graph tangent and cotangent, just like we graph sine and cosine by plotting all the points and creating a graph. So you still have some time, maybe only 5 minutes. It's like my clock back there. But see if you can like try and start the graph. Try and get that graph drawn, at least a little bit, where it's like starting at normal. Goes down, it's going to be a sine graph instead of a cosine graph. So your graph should look like a sine curve instead of cosine. Well, I mean, it's just your y-axis. So because you can pick where you want. Correct. Because it's a continual, so it's just you're moving that. Because you're just changing your phase shift. So whatever that phase shift is based off of where you're starting on the side. Yes, that's your sinusoidal axis. So that's the same tool. It would as well. Because when you're at the beach, help if you looked at it?
Little. I usually help you like grasp.
Grab it. Yes, yes, yes. So like the whole, it's gonna end at 15, but like you're gonna have a halfway point at so split it.
And I can start it at like 0.
Yes, exactly. Okay. Okay, so everything is, remember, everything's equal amounts. So if I have 0 to 15, that's half. Oh, it's just, yep, it starts at 0. Again, it's times half. So like, if earthquake happens, you hit your stopwatch, and you're waiting 15 minutes to come to the other. So you have 15 minutes. Yes.
So,
Yeah, how do you?
Well, okay, so how do you
The water's actually resting, yes, and the water's resting on the ball.
add 10 times? So what would you do to get
So,
But don't they only get up to
No.
Yeah.
The
No.
normal depth is 9. So it's
the
starting
amp
at
would
half.
take the final test. Not it
Yeah.
goes up to so that's the distance between
So that's 9 to 9.
that's fine.
No, she's supposed to sign her.
I'm
Oh, there you go.
wait, cut that in.
Wait, it's supposed to be. It's going down and then has to go back up to the normal.
Well then
No, you're right, but it just has to go back up.
no, because that's the
No, that's fine. Yeah.
it has to be flipping.
9 is the beginning, not
Yeah.
Look at that. You love to see it. Here's game.
Ooh, 53?
As of 15 here.
All right.
Can I sit down?
Where's your toilet?
I put it back.
All right.
Bring his ear. I'll go back.
No, don't bring it back. I was so high on adrenaline.
Dude, I could tell. You were like you kept like flinching.
Do you know Mrs. Perry or
Miss
Mrs. Palmieri? Is she easier than Mrs. Perry?
I
I
don't think
usually
I
say
actually.
better.
Do you not
I've
actually?
heard she's more lenient on side Perry.
I heard you heard it even.
Yeah, our
Have a fantastic day. Actually, have a great weekend. I keep forgetting.
It's so exciting.
No, I'm not forgetting.
But it's like a little present every time.
Mm-hmm.
I don't have to work it.
It is. It's like,
Yeah.
ooh. Hey, how is that job going?
So far, really good.
So far, good?
I burnt meatballs yesterday.
Okay, that's not so good.
It was. I got the eat them all.